Good day. For those of you who do not know us, we're the instructional staff for ECE 150. Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to work through an example of using dynamic memory allocation. So in this topic, we will again be discussing the lifetime of dynamically allocated memory. We will author and discuss a program that requires repeated memory allocation and deallocation and be responding to such demands as results of external need. That is, we do not know a priori at compile time how much memory is actually required. We will solve the following problem. Suppose that we are reading data. We're actually going to read it from the console, but you could be reading such data from a sensor. We will not know a priori, that is, at compile time, how much data there will be. There could only be one datum. On the other hand, there could be 1,000 or 1,000,000. We are going to have an appropriate amount of memory to store this data. The problem is we don't want to waste too much space. There's no point in wasting an array of capacity 1,000,000 if there's only going to be 7 data points. Now, we are going to require one helper function. We are going to be printing out an array, so this is a very simple helper function that prints out all the entries of an array. Alright, here's the basic framework of our program. We're going to allocate some memory dynamically for the data storage. Now, we don't know what the capacity is going to be yet, but there will be some initial capacity. Then we have this infinite loop. It's going to keep on executing, continually asking the user for more data. It will only break after the user enters a value that is less than or equal to 0. If the value x that is entered is not less than or equal to 0, we will be required to store that new datum x in our array. Once this while loop is finished, all we're going to do is print the array and then delete that array. Of course, in reality, you may actually want to do something useful with that data, like analyze it, but this is sufficient for this example. Alright, for our initial setup, let's just start with an array of capacity 10. This capacity may have to change over time, but there's no reason not to start with some small number like 10. Now, there's an interesting thing here, however. While the capacity of the array is 10, we have not yet entered any data into this array yet. So we're going to have a second local variable that keeps track of how much data the user has actually entered. Okay, so to store how much data has actually already been received from the user, that is, how many entries have been filled in the array, we're going to have a local variable data size. So capacity is the total number of entries the data can hold. The size is the total number of datums that the array actually does hold. This naming convention is used throughout the standard template library. So if we were to execute those 3 instructions, or 3 declarations, we would have an initial setup as follows. In main, we would have 3 local variables. The data capacity is initialized to 10. When we called new and initialized the data array, memory was allocated for 10 entries somewhere in memory, and that address was returned. So we can see that array over here on the right hand side. Now, we can now refer to those 10 entries using data 0 through data 9. The data size is initially 0. All right, so with our initial setup, we now have the following at the top of our program. Now, once we get into the while loop, there is a local variable x declared, the scope of which is restricted to the while loop. The user has entered in a value, 3.6, and now we have to put this information somewhere. Specifically, we want to put 3.6 into the entry data 0. Following this, the size must be incremented to 1. Now, you may initially think that this requires another index that tells us where we're going to be storing the next datum. However, fortunately, data size already tells us where to put the next value. If there are data size entries filled up so far, then the next value has to be placed at the array index data size. Data size is 0. The next item has to be placed at data 0. After that, we can increment data size to 1. Consequently, focusing on the loop of our program, we've requested a value from the user. If it's less than or equal to 0, we break. Otherwise, we will store that value at index data size and increment that local variable. All right, let's watch the first few steps. And by the way, you might be able to see some of this in your debugger if you were to use that debugger. Okay, so 3.5 is stored in data 0, and then we increment the data size. Now comes the next value of x, 3.7. It's not 0, so we store 3.7 in data 1, and we increment the data size. Next comes 3.6. We store that in index 2 of the data array, and then we increment the data size. So at this point, there are 3 objects in the array occupying indices 0 through 2. The next value comes 3.9. It's stored there, and data size is incremented. 3.8 stored, increment. 4.0 stored, incremented. After 10 steps, the data array is now full because the data size is equal to the capacity. However, we now have another value to store. Where are we going to store the value 4.8? We only asked for an array of capacity 10, so we cannot assume that we can store anything at the address 4B99-3B10. All right, what can we do if the array is full? We can't expand it. Strategy. We could request a larger array and then copy everything over from the current array into this larger array. All right. So here we have the current array that is full. We could request a larger array, copy the 10 items over, after which, of course, we no longer require the original smaller array that is currently full. So again, focusing on this loop, the user has entered the next datum. However, if the array is now full, that is, we've entered in as many values as the array has a capacity for, then we have to do something. We have to increase the array capacity in some way. Once we've done this, then hopefully we can just continue executing the next statement to store the next datum in the next available entry. But we have to increase the size of the array first. Alright, so first of all, we have to determine what we're going to do if the capacity is full. We could either double the array capacity, that is, get a new array that has twice the capacity of the currently existing array, or increase the capacity by 10. Each of these solutions have pros and cons associated with them. For example, if we double the array capacity each time it is full, then we will not have to do that much work on average. However, there's the potential for a lot of wasted space. On the other hand, if we only increase the capacity of the array by 10 at each step, then every 10 entries that are entered require us to fix the problem of a full array. We're going to choose the first. We're going to double the capacity of the array. So, if the data size is equal to the data capacity, we will double the data capacity and then allocate a new array of that larger capacity. Once we've done that, we can copy everything over. Alright, let's try that out. So we've doubled the capacity. So now the data capacity is changed from 10 to 20. We now assign data a new array of capacity, of that new capacity, and so that is the result of the call to new. It has found 20 times 8 bytes that is sufficient memory for an array of 20 doubles, and the first address is returned and stored in the entry data. Okay, now, do you see a problem here? We'd like to copy the old data into the new array, but unfortunately, we no longer have that address. So we no longer have the address 4B993AC0. Because right now, if I access data 0 through data 19, I am now going to access only the array that we just now allocated. In other words, we just ended up with a memory leak. We have the first array still allocated, but we have lost its address. So the question is, can we store the old information first? Well, of course we can. This just requires a few local variables. So we can declare another local variable, old capacity, and that is initialized with the current capacity of the array, and we'll have another pointer to a double, old data, and that is initialized with the address that data currently has. So that means that old data will also have the address of the array that we have previously allocated. Only then can we double the capacity and assign data a new array of that new capacity. Alright, let's execute these four statements that we see above. First of all, we have two new local variables that are declared. So sufficient memory is allocated on the stack for those two local variables. Old capacity is initialized with the value of data capacity, and old data is initialized with the address stored in data. So now both data and old data refer to the same location in memory. So consequently, if we were to access data 7, we would get the value 4.4, and we could also access data that same location in memory using old data with the index 7. Alright, next we double the capacity and we call new with that doubled capacity. So the operating system finds 20 times 8 bytes, and it returns the address of the first byte of the first entry of that new array. So that is what is assigned to data. All right, at this point now, if we use data as an array, we are now accessing the new array of capacity 20. Whereas if we want to access the original array, we would access it through the local variable old data. Okay, now we have to copy the old information over. We have stored the information about the old array, we've allocated memory for a new array. So now we have a loop. That loop will go from 0 up until the old capacity, as that's all we have to copy, that's all we have to copy over. And we will set data k to be the original data in the old array at that location. All right, let's run this for loop. This for loop has a loop variable k, the scope of which is restricted to the for loop. It's initialized with 0. We then run the loop, and with every single iteration of the loop, we copy over one more value from the old data array to the new data array. At this point, the loop variable k is equal to 10, which is equal to the local variable old capacity, so the loop terminates and the local or the loop variable k goes out of scope. We have finished now allocating a new array, copying over the old data, and the conditional statement that you see above is finished. So any loop variables inside that conditional statement also go out of scope. At this point, we are left with x. X is the next value to be stored in the array. Where do we store it? Well, data size is equal to 10, so let us assign data 10 the value of x. At this point, we will increment data size, and so data size is now 11. We can carry on, and now we can continue to fill up the new array until the data size is equal to the new capacity, which is 20. Now, does anyone see any further issues here? Well, we still have the old array allocated. We have not yet deallocated the old array, but we no longer have its address stored in any local variables. We have a memory leak. So what do we do? Well, the old array is no longer required once the for loop is finished. All the information in the old array has been copied over, so consequently, once the for loop is finished, we no longer need the old array. Now, when we call delete with the square brackets on the old array, all that does is tell the operating system, hey, we don't need that old array of capacity 10. The operating system then says, okay, it flags those 80 bytes as now being available, and we're just going to be careful. Even though old array immediately goes out of scope, we will nevertheless set old array to null pointer. All right, so here is the loop within the larger context. The user enters another value, and if the data size is equal to the data capacity, that is, if the array is full, we store information about the current array, allocate a new array, copy everything over, and then delete the old array. Once that's done, we can just continue updating the data array as we've assigned data a new array that has larger capacity. All right, that's it. That is the entire program. So, following this topic, you now understand, hopefully better, the process of dynamic memory allocation and deallocation. You know that you must keep track of all previously allocated memory until it is no longer required, at which point you can deallocate it. You are aware that all addresses of any dynamically allocated memory must be stored in local variables in order to access them. And you now have reinforced your understanding that once a local variable goes out of scope, any information it may contain is gone. Here's the references, the colophon, and a disclaimer. Cheers!